my mind. Scribbled theories they all refuse to find. I've been working on energy for a brand new day, but even in the crowd I'm still a castaway. Alienated from the A's of added nature in disguise. Ideas ahead of time dismissed with narrow eyes. Benefactor boy, dreaming about the world you can't deploy. Changing the system, but treated like a toy. Ideas misunderstood, but brilliance is his boy. Benefactor boy, can't you hear his voice? Talk team up 0 point, the points lost on them. Kevin structures crumbling from the same old sim. They laugh like I'm crazy, but I see it all so clear. Exploited labor, unheard injustice, burning ears. Fighting for a change in this wasteland of noise. But they call me foolish, wanting shed boys. Benefactor boy, dreaming about the world you can't deploy. Changing the system, but treated like a toy.
All right, welcome, and welcome back to Beneficence TV Live. Today we're going to do a quick lecture on 2 modified versions of the Jewel Thief circuit I've been working on, trying to, in my attempt to try to close the loop, either fully or partially. And after that, we're going to take a quick break, and I'll set up the lab, and we'll do some quick experiments. I might try to test some of these ideas. I might just take some readings and see where we're at in terms of what we need to supply the battery with power. Now I have a capacitor set of different kinds of capacitors, but at the end of the day they might not be sufficient enough. So we'll run some quick calculations with the simulator. I'll show you guys the modified versions of the Jewel Thief circuit that I've been working with, and we'll jump into our lecture. So the first modified version of the Jewel Thief circuit, the ABHA excitation circuit, is called the pre-driver circuit. Okay, I wanted to try to incorporate a MOSFET instead of a traditional transistor. Okay, so a MOSFET stands for metal oxide semiconductor field effect transistor. Now, I believe it uses a field effect to switch the transistor instead of a mechanical switch, which should allow it to switch faster and cleaner, providing a higher Q factor. So that's exactly what we need. But in order to do this, we need a higher gate voltage to trigger the switch. How do we do this? Well, I was thinking, and we can try to use what's called a pre-driver, or a basically, to summarize, the original Jewel Thief uses a single small transistor to switch the current for the coil, right? This produces high-frequency pulses that light an LED lamp, LED or a lamp. But switching speed and voltage tolerances are limited with these kinds of transistors. Now, my fix employs the use of a low-current small transistor to trigger the MOSFET. And I call it a pre-driver. The reason for this is the MOSFET needs a higher gate voltage to start the switching process, which a small transistor can theoretically provide efficiently. The MOSFET then replaces the main driver transistor as the oscillator for the circuit, allowing for faster, cleaner switching that leads to potentially a higher Q factor, which means more efficient resonance, stronger, more precise pulses from the coil, more energy delivered per pulse with less loss in the switching device. So think of it like using a small starter motor to turn on a bigger motor. The smaller device controls the bigger one without being stressed too much. I'm going to show you that briefly, and we'll go over that in a minute before we start our lab. That's the wrong one. There we go. So you can see here, I have the pre-driver right here, the regular transistor, just a low current driven one. And then I have the MOSFET And we'll get into the connections and everything, but it does seem to work. So that's exciting. I haven't specifically chosen a MOSFET or a pre-driver transistor, and some of these values need to be adjusted, right? Because at the end of the day, this is using a traditional transformer, and we can only simulate the rodent coil to a certain extent because it just doesn't include the variables included with the unique phenomenon associated with the coil at specific configurations. And now what I mean by that is you can actually get from a 1-to-1 ratio of transformer, because these coils act as a transformer as well, you can actually step up voltage quite a bit, 10 times or more. I've seen more than 10 times very easily when you achieve resonance with the coil. So there are certain unique phenomena that happens with the coil that's not actually well documented enough to be included in the simulator. So this is probably as easy as going in and making a few adjustments and adding a few options to the transformer device we have here. But at the end of the day, we're going to have to kind of improvise a little bit, because we are dealing with a unique situation where the simulator is just not capable of accurately simulating a rodent coil. So we have another modification that I was working on, specifically trying to close the loop. Now this is an exciting one, and we're going based off of the work of people like Lieutenant Colonel Tom Bearden, John Bedini, who all emphasized specific characteristics in your system in order to achieve what they call overunity and closing the loop with that overunity. Now, this part remains the same conceptually, right? We're taking energy from the coil, capturing it with a capacitor, and feeding it back to the battery via a diode and a resistor. Pretty straightforward, actually. But the timing is crucial, right? So energy only flows back when the spikes are high enough to overcome the battery voltage plus diode drop. This second modification is all about recycling energy back into the battery while the device is running. This is very hard to do. Normally what you want to do is rectify the energy and put it in a cap bank and then dump that bank back into the battery. We're doing something similar. We're using a diode to kind of rectify, and this is a recent discovery or realization really that I made when doing some research on diodes. Apparently they do act as rectifiers for specifically filtering out some of the forward EMF going backwards into the battery. So that's important. So that's an important characteristic that I didn't consider. But in a normal, going back to a normal circuit, the pulses generated by the coil are mostly delivered to the load, the lamp, the LED, whatever you're powering. And then the battery slowly drains, okay? In this modification, I'm attempting to build the circuit in such a way that if any excess energy is coming off of the coil, it is then fed back into the negative side of the battery. Now, I've tried to do this, actually, with a rectifier and a cap bank. But the rectifier just destroys all the current, and there's basically no voltage, no potential either. So it wasn't even enough to light that 0.5 watt LED light bulb that I have, the oscillating one, that basically anything can light it. Such a low amount of power required to power that thing. So it was kind of disappointing, but then I was thinking about it. Okay, so I'm using high-speed diodes already. If diodes are acting as a kind of rectifier of some sorts, maybe that's the kind of rectifier I need. So let's work with the single diode, the high-speed diode, to cap bank and modify it that way. So imagine going back to a traditional circuit. Imagine a racetrack for energy, right? Normally, energy leaves the battery, goes around the track, from the coil to the LED, and then it stops at the LED. Closing the loop is like adding a return lane for some of the back EMF that's stopping, right? Some of that energy makes a full lap back to the starting point, the battery, instead of stopping at the load. This allows the battery to regain some of the energy it puts out, effectively reducing net drain on the battery. And look, I know this is somewhat confusing, so let me break it down in this way so it's better, easier to understand. Closing the loop is like adding a special return lane, as noted before, just for the extra energy the coil makes, right? The extra energy is called back EMF. In a normal circuit, current leaves the battery, goes through the load, and then comes back to the battery to complete the loop. This creates the dipole that Tom Bearden emphasizes that you cannot destroy. That's normal current, and it doesn't give the battery any extra energy. It just flows like a water in a closed pipe. However, in our system, the back EMF is like a rebound or splash from the coil. We give it its own lane back to the battery, separate from the normal current. So it doesn't fight the battery's forward push, right? We're kind of directing it in a different way back to the battery. The load still gets the main energy, the AC from the coil, but this energy can safely return to the battery without fully destroying the dipole. Theoretically, at least. That's what we think. This is why we say the loop is closed or partially closed. But it's not the same as a normal circuit. It's recycling the leftover energy in a way that's, not wasted. So we're talking about something different than just circulating the current and creating the dipole. All right? And the dipole, remember, is the different potential between the positive and negative terminals on the battery. The system doesn't violate physics. Remember, we're not creating energy from nothing, okay? The laws of energy of conservation and entropy still apply, but only to closed systems, not open systems. So think of water wheels or wind turbines or even heat pumps. These devices all put out net energy gain because they require little to no input power. Yet they do not violate physics because they are differentiated as open systems, open to the reactions of the environment, open to reacting to the fundamental forces of our universe, the strong force, weak force, electromagnetic force, and gravitational force. These can all be utilized. So what we are doing is essentially capturing pulses that would otherwise be wasted as heat or radiation and redirecting back to the battery. The magic is in the timing, really. The pulses must arrive exactly when the battery can accept them. Otherwise, the loop doesn't conduct at all. So what this looks like in practice is with the MOSFET, the metal oxide semiconductor field effect transistor, and pre-driver setup, the coil produces, or theoretically can produce, fast, tall, clean spikes, right? Remember, the Q factor, the quality of the resonance is important. You can have resonance, but it can be shit quality, right? Remember the analogy of the guitar string. If you pluck the string really hard, that initial pluck is a sound, right, that you're intending to make. But there's reverb going on if you pluck it too hard, where it's wobbling back and forth from its own momentum. And that's producing reverb, extra sound. That's extra energy that can be distorted, right? You want a clean, smooth, and steady pluck. Instead of a bow, you want to bow, 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 bow. You want to clean out the pulses so that when they combine and the waveforms combine into coherent waveforms, they don't combine destructively or produce any kind of destructive interference. Now, with the closed loop capacitor diode resistor setup, theoretically, some of those spikes should return energy to the battery, reducing net drain or even stopping it, maybe. So we're going to maybe try that on the... I've set something up on the simulator. It appears to work, but it might need to be adjusted in real life for my system. We might try to do some tests and see if we can actually implement some of these ideas tonight. So let's get into the last part of this lecture, is why all this really matters. Well, this can demonstrate efficient energy recycling in small electronics. Very simple stuff that everybody can do, get their hands on. It's not some complex idea that only, you know, like somebody with a doctorate can, or a degree in engineering can wrap their head around. It's a simple example of high Q pulse-driven systems, right, that capture back EMF and use it constructively. So for anyone curious about energy harvesting or fringe electronics, fringe science, it shows how timing and clever feedback can actually improve efficiency, and very easily too, given you have the right geometry of coil. Now, remember, the dipole theory, okay, going back to Tom Bearden, he emphasizes, don't destroy the dipole, right? You want to maintain that potential difference, but by returning the forward current back to the battery, you are destroying that potential difference because it's stabilizing, right? It's stabilizing that difference. That's what nature does. It evens out. It stabilizes. So if, say, you have, you know, a potential difference of 12 volts on the positive and negative, that's going to stabilize until it's 0, right? It's like, think of water leveling out. So you don't want to destroy that because that's what creates the energy. So if you can run a system without destroying that potential difference, that's what Tom Bearden emphasizes. Now, my system might not be maintaining the dipole entirely, but theoretically, it could be depleting it half as fast with the synergy between the forward and back EMF. Now, what I mean by this is that in a normal circuit, the battery pushes the current through the load, and energy leaves the battery, slowly reducing its potential difference as it stabilizes between the two terminals. The dipole naturally dies over time because its existence is dependent on that potential difference between the positive and negative terminals, right? So in our system, the coil produces back EMF when its magnetic field collapses. This back EMF appears to be flowing back towards the battery in a controlled way, creating a rhythmic oscillation where the forward EMF from the battery and the returning back EMF chase each other in just the right way to produce what I call a synthetic AC. Now, synthetic AC is nothing new. I mean, it technically does exist in two systems already, in regenerative braking systems, which aren't very efficient at capturing that back EMF, and with resonant converters, right? So, however, it is important because they don't differentiate between that kind of AC created between the synergy between the forward and back EMF, and regular AC just created with forward EMF bouncing back and forth. So that's a distinction that needs to be made, and it hasn't been made. So far, mainstream science is just lumping these two into the same category, and it's kind of deceiving people as to the potential efficiency effects of these kinds of systems. Whether that's intentional or accidental is up to you to determine. Either way, I digress. Let's get back into it. Okay, so the back EMF and the forward EMF chase each other in such a way that that pulsed DC creates a synthetic AC between the two effects. This superposition of forward and back EMF pulses effectively recycles energy that would otherwise just be lost, right? Giving the battery a gentle push each cycle where it would otherwise not have one using the forward EMF alone. The result is that the battery's potential difference, or dipole, might be maintained longer than in a normal circuit, given that our observations are like 15 millivolts drain on the battery, powering this, 40-watt panel at, 10% brightness for 15 plus hours on 12.2 watt hours of energy. Insane. Like, that's pretty good efficiency. Again, it's really hard to gauge the efficiency of a system like this because our meters aren't meant to read the negative energy, right? If you're collecting negative energy from the vacuum, remember, negative energy is that little bit that rides on top of the back EMF spike, right? So back EMF has the potential to have that radiant spike with it, but it doesn't always, or it doesn't always have a usable spike, rather. So, by using that back EMF correctly, we can actually increase that radiant spike riding the back EMF wave. So the result is that the battery's potential difference, or the battery's potential difference or dipole is maintained longer than a normal circuit, right? It decays more slowly because the energy is potentially replenished by that back EMF force, or back electromotive force. This theory is supported by the evidence of my system only draining the load about 15 millivolts, right? That's pretty good. And that's only with the introduction of a high-speed diode on the positive rail again. So we were getting good efficiency before the diode, but we introduced that high-speed diode on the positive rail of the output, and it not only increased the brightness, but it didn't increase the drain on the battery, meaning it output more of or redirected more of the energy, right? It's using more of the energy and not wasting it. So I'm going to jump over to the workstation, and I'm going to show you a couple of these circuits before we get into it. So Mike says you can't use a standard rectifier with flyback. You need to make your own rectifier with HV diodes or high-speed diodes. So that's an idea too. We can try to make a rectifier with all high-speed diodes. I don't know if I tried that last time because remember we were on. I think you were there too, Mike. We were on the other Mike K from Faraday Research. We were on his show, and I think I was running some tests in the background in a lab, and he was suggesting that I use a rectifier and dump that energy into a cap bank, which is usually standard practice for these kinds of free energy devices when you're attempting to close the loop. However, it just seemed to destroy the current, and I was getting almost no voltage either, at least not of the kind that I was getting before. And then I did get the voltage to go back up, but the current didn't. So you're absolutely right. Maybe I don't think I had the high-speed diodes then, but we might be able to try to build, maybe not tonight, but maybe on a future live stream, we'll build the high-speed diode rectifier. Yeah, that would be fun. That'd be very, very cool to try. I think you might be right on that because I didn't consider that they need to be high speed to catch the high frequency. All right, so which one are we gonna do? Yeah, let's start with the pre-driver circuit, because this one is the one that I actually am most excited for, because once we get this one working, this is going to be the most efficient design, in my opinion, if we can get it working. And then once this modification's working, we could just combine them, and we'll have this one with the closed loop or partially closed loop if we can. So let's run the simulation. And see, I'm having a problem with the base overheating a little bit during startup. I'm not really sure. It doesn't matter what I lower this to. I think it's the same. Let's see. Let me try increasing it, actually. Maybe that's why. Yeah, it doesn't matter what I change the resistance value. Maybe I'll change the pot. But the pot, this really is what the resonance is dependent on. So this state right here, you can't really change the pot. Once you found the resonance, you found it, and that value has to stay. But yeah, it doesn't really matter what I change the base resistance to. It still has this kind of overload at the beginning. I'm not really sure if I have it hooked up wrong. But see, now after a while, after it cools down, it starts. So I have something a little too high, or something, some resistance is a little too low on the base or something. I'm not really sure what's going on. Maybe I need to lower this one. Or I'm sorry, raise it. Oh, I keep saying lower. 5K. That's a little better, 100K. Let's keep that 1K because we want that flowing good. Nice, switch nice and fast. That's what we want. We want them both switching nice and fast. So you can see they're switching now. I think actually that solved it. Let's try to increase this more. I don't know if increasing the resistance too much though is gonna throw off the fucking frequency here. We're gonna have to readjust the resistance on the pot. I mean, we could always try it and see. 500K, shit. It's a lot of resistance. I mean, it's only overheating for a second now. 1 mega ohm? No. Because that's a 1 mega ohm pot. Yeah, that's not gonna work. Oh, there we go. I accidentally put the small character value, which is a different scale. I think it's milliohm, but we're looking for mega ohm. I mean, 500K was better. It only... Or was it 100K? Something only lit up for like 2 seconds. Yeah, it was 500K that was the best. It's still overheating a little bit. Maybe I just need to have this like a really high rated resistor, like a 2 or 4 watt or a 5 watt resistor, something like that. Hey John Gray, nice of you to join us this evening. All right, so I also with this circuit I was messing with the waveform because I believe you want to get the current and the voltage 180 degrees out of phase. So what that means is when the voltage is going down, the current is going up. And that's exactly what we see here. But it's not even, and it's like the wrong kind of value for the capacitance maybe, but you can see it wants to. It really wants to start oscillating, and if we can get that to start oscillating, that means we really have something. So right now it starts to oscillate a little bit in a very mouse-shaped way, or slightly mouse-shaped way, and then it kind of just dies off. So that tells us it's close, it wants to, but it's not the right value for the right to produce the right frequency. And it's unfortunate because the frequency reader and this simulator is broken or something. I keep trying to enable it. I go into properties and I show frequency and it's not there. I'm like, okay. So that makes it a little harder but we can still get a visual guide of where the current's going to run, which is exactly what I needed because I'm a visual learner. And look at this. There's barely any current coming from the power. That's exactly what we want to see. Oh, actually, no, it's being redirected here. So let's actually, that might actually, yeah, it seems like it's bypassing this base altogether. Let's try disconnecting this. Yeah, and see that the switching stops going fast. Because the base is switching on and off, and then it's opening the connection between the collector and emitter. Let's see. Damn, look at channel B though. Look how fast channel B is switching. That MOSFET. And this is barely. Maybe that's what we want. Maybe we'll want this going as slow as possible just to trigger this just enough, because that would use the least amount of energy. If we could trigger the MOSFET with the lowest and slowest amount of triggering from the pre-driver, I think we might have something there. I don't know. What do you guys think? Oh, Mike asked if I'm running that light off of the vortex coil. Yes, absolutely. And 12-volt battery, 20 amp hour. It's bright as hell now. I tuned in the resistance of the base a little bit more. And while it's powering it, we're getting 20 extra volts out, right? So we're reading 20 volts on the output while it's powering the load, which is a 40-watt panel. Now it's maybe about 10% bright, but still, it's pretty damn bright. For the amount of power that we're putting in is basically nothing. So Mike, you're the circuit expert. What do you think? If I disconnect this goes slow, but I'm still getting a lot of speed coming out of the battery. Don't we want like a little bit of trickle coming out of the battery? Oh, I know why. This is fucking connected wrong. Is it? No, it's connected right. We get this overheating a lot, but this goes up. Damn, that actually was faster at cooling down. Let's try removing that. we're still getting a lot of heat. So where do you connect the collector of the pre-driver then? Maybe it just goes to the base and that's it. No. Slow down the current. Slow this current down so we can get a better idea. Okay, so now this is switching faster than the MOSFET. We don't want that. We want the MOSFET to switch faster than the pre-driver, I believe. There we go. That's too much. Well, we got the pre-driver right now. Switching on the MOSFET at the slowest speed. Can actually probably test that out and see, okay, well, that actually triggered that at 1 volt. Let's see what the simulator does. Yeah, so it's not going to trigger at 1 volt. But the current's still flowing. Wait, hold on. Is it? Yeah, it's still triggering the MOSFET at 1 volt. So we actually don't know. Threshold volt. Oh, here's the threshold voltage. Shit. What's the threshold voltage though? We want that. I think we want that at least. Let me double check. I know at least 20 volts. Or at least above 12 volts. Because we want that pre-driver to up the voltage a little bit. So let's actually try 15. Yeah, see, that's still... interesting. So now we have no switching of the transistor though. Okay. There we go. Okay, so that works. So let's set this threshold to 12. was weird. Okay, now it's actually stepping up the voltage now like it's supposed to. Interesting. But it's going back down. Maybe that might be the capacitor storing and then dumping. I guarantee you that's the capacitor storing and dumping. Yeah, we changed the capacitor value and that goes away. Oh, now it's, oh. Yeah, so, okay, good. Yeah, so that is the capacitor. Interesting. Yeah, because with that there, it just hangs around 10.9 volts. So apparently it is switching. Not fast enough though. Let's remove this capacitor for now. Change this back. So what we're going to need to do for our base transistor is figure out how much voltage it's going to output, and then match our MOSFET to that MOSFET gate threshold to that that voltage. So I'm not sure it's going to actually the pre-driver might not step up the voltage. It might just provide enough voltage to trigger the gate. I'm not really sure how it works, but at least it's triggering. That's a good thing. And the even better thing is, it appears it's triggering the gate with a slower current speed than the gate's being triggered. Or the gate's triggering its drain and source. So the MOSFET is switching faster than the pre-driver, which I think is what we want to see, because we want to use as little possible energy. We're just triggering it, right? It's like John Bedini with his SSG. You want to use just the lightest amount of current to just tap the coil so it starts working, and provide that gate threshold voltage to trigger the oscillation. I mean, if this is what we're supposed to be looking for, hold on, we got this to go slower by increasing this. Let's do 5K. Yeah, see this? Like twice as fast. Let's see if we can increase a little more. Let's do 10K ohm. Yeah, so it still appears to be triggering. And this is going way faster than the current going through the pre-driver. Okay, so if this is what we're supposed to be seeing, then it should work. And the problem that I had, I guess, was I hooked the base directly up to the collector of the pre-driver. Maybe that was not supposed to be a part of this system. The only concern I have is that it's coming really fast out of the battery. Now we want it to return to the battery at the speed that it's oscillating, but in terms of pulling it really slow from the base, or yeah, I'm not sure. What do you think, Mike? Do you think we're supposed to be seeing something like that? That fast current being pulled from the battery, or you think that should be slower? Like the trigger here. Oh yeah, so get this. I discovered if you put a 1 farad capacitor in parallel with the load here in this circuit, look at the fucking current. Look at this. Look at the fucking current. It spikes at 1.38 kiloamps. Like, what the fuck? And if you adjust this, you can actually get it to oscillate a little bit in the kiloamp range. Like, that's probably why this shit's overheating so much. And I have no idea how to cool it down unless this isn't going to heat up in our system because we're using the negative current. I mean, we're also using the positive current, so it's maybe it'll be less hot. I'm not really sure. What we can do actually is add a resistor and see if it burns out at the correct threshold. I feel like we've already ran that test though before. I feel like it actually lasted long. Yeah, we did run that test and it did last a lot longer. I swear to God, we ran that test on live stream once. Yeah, if I remember correctly, I believe we ran it and I believe it lasted a lot longer than the threshold said it should have with the output that we measured at least. Yeah, I'm pretty sure. So maybe the heat won't be actually a factor. Who knows? Fry it and find out, I guess is what Nathan always says. He might be right on that one. But it is switching fast. This isn't normal speed. Normal speed's like 50% here. And this one's, the MOSFET is switching faster than the pre-driver. We might actually be able to get that to go down more. Let's see, 500K. Let's go back to 500K. Yeah, after it cools down, there's a huge speed difference here. This is exactly, I think, what we want to see. I'm not sure if this is the resistance value we want to add, but mechanically speaking, the electrodynamics of it, we want to see, in my opinion, that's what I'm thinking at least, we want to see the MOSFET switching faster than the pre-driver because we want to just touch that MOSFET and trigger it with the smallest amount of power. But that actually, it might be too high. Let's pull it back to 10K. All right. I think I've shown you enough of that. If you guys want to mess with it further, I'm going to put the link in the chat for y'all. Okay? Oh shit, I can't put it in the chat. It's too long. Fuck. I'll put it in the comments. I'm going to put it in the comments. That's what I'll do. So I'll go to the comments section right now and just refresh it if you don't see it. Put it in the chat. It's too long. Oh, does it not let you comment on a live video anymore? I'll have to put it in the comments after the video. That's unfortunate. Oh, it's so useful, John. It's like the best. Like I can actually visualize the current flow now, and that's exactly what I needed. 'Cause that's what helps me. That's honestly that's what helped me visualize inform the synthetic AC hypothesis. You know, thinking about how the current's actually running through the system. But with that said, we're going to move on to the next circuit, which is another modified joule thief. But this one is attempting to redirect some of the energy in the circuit back to the battery. So you see here is just the standard setup with the single transistor, very similar to what we saw earlier, a little bit simpler. This is so this might not be necessary if I can figure out how to get that voltage to go up again past 12 volts. This won't be necessary, but this is just an AC supplement. It's a AC, it's called an AC source. So what it was doing is, here, I'll show you. I'll just show you. It's easier to show you. Oh shit, is it actually not? Oh, never mind. So, I guess maybe I fixed it by rerouting this wire. So we don't need this supplement. Anyways, so that was just because I couldn't get the current to flow through this capacitor here and back into the negative terminal of the battery. So this right here, this lower corner, this is actually the new addition that supposedly will help close the loop. Might not completely close it, but maybe partially close it and redirect some of the lost energy back to the battery and charge it at the same time. Yeah, so here we see, and I'm going to mess with this, fry out your shit. It's not good. Let's try a different value. Okay, so yeah, so see, we have too small of a value now. We lowered it down to 1 nanofarad. And because we did that, there's not enough storage in the tank for the current to flow. There's too much resistance, and there's not enough space for it to flow. So we increase that to, what do we have it at, 1 microfarad. And then we suddenly get that flow to start again. And that's exactly what we want to see. And honestly, I don't know if we want it to go back into the battery too fast. Like, I'm good with it going slow back into the battery, because again, when we listen to John Bedini, he says that the negative energy is slow at recharging the battery. So if we're going to recharge a battery with negative energy, theoretically, based on his advice, we'd want to do it slowly. But let's see how this, I didn't pay attention to the voltages. Let's see how this affects the voltage. It doesn't seem to affect the voltage on the light too much. It's still lighting the light, and the voltage is still going up, albeit it's a little slow. We might be able to increase that with a capacitor here, bridging the collector and the emitter. Let's put that back, because that doesn't seem to affect it. Yeah, that negative connection back to the battery doesn't seem to affect it. Right now, it's not really going to simulate any net gain, right? If that's possible with our setup. What it's going to do is it's going to tell me if this is not going to blow up the shit. It's going to tell me if this is going to work or not. And it's going to give me an idea of the current direction. So this isn't necessarily going to tell us, oh, we can get over unity or anything like that. This is just going to make sure, like, I have the right setup and the current is going into the negative correctly. And it's not going to blow up my shit. So yeah, let's put a capacitor there, see if we can get that to charge a little faster. And now we're not getting any kind of, yeah, it's just all being sucked into the capacitor. That's too big. Way too big. Let's try picofarad. Alright, we're going to scope this. Maybe let's try lowering the resistance. That might. So first, let's disconnect this modification because we want the voltage to be able to go up fast. So let's get the voltage to go up fast, and then we can work on the modified version. That's so weird. Why is it taking so long to get this voltage up? I don't have a capacitor here.